so let's do one more ice table problem. This one is a little bit more complicated, so we're going to do the quadratic equation. How many of you know about the quadratic equation? I'll get a show of hands. Quadratic, have you heard of it? Okay. Well, the quadratic, that's good. The quadratic equation will not be on the test, but I'm going to go ahead and do it, and we'll do the entire problem together. But the point being the quadratic equation, which you need to solve this ice table problem, that will not be on the test. What will be on the exam would be the math. The math that will be on the exam will be more akin to this, okay, this type of problem, which is what we did on Wednesday. The one where we had to square root both sides. So that's going to be on the test. The mathematics here will not be on the exam, but I'm going to solve it using the quadratic. Right, so at 1280 degrees C, the Kc for the reaction, Br2 goes to 2Br. Is this an equilibrium? Yes or no? Okay, very good. Okay, we see the back and forth arrows. This tells us this is an equilibrium reaction. And the Kc for this is 1.1 times 10 to the minus 3. So let me just rewrite this here. And this equilibrium constant is 1.1 times 10 to the minus 3. The initial concentrations. The initial concentration, we want to underline the word initial, is 6.3 times 10 to the minus 2 for Br2 and 1.2 times 10 to the minus 2 for Br. Calculate the concentrations of these species at equilibrium. So, first of all, what is the equilibrium expression for this? Okay, it's going to be products over reactants. Remember? Products. What should we do with that Br? Okay, we see a 2 by there, bless you. We see a 2, so what does that mean? Okay, products over reactants. Bless you. Okay, concentration of Br2. What should we do with that Br2? Raise it to the 1 power. Right, so a lot of students mistake this. Okay, gotta remember this is squared, and the square comes from the 2 coefficient when you balance the equation. This is called the law of mass action. Right, so this Kc is given to us in the problem as 1.1 times 10 to the minus 3. Okay. That's Kc. And the Br2 is 6.3 times 10 to the minus 2. I'll just go 0.063. And this is Br, this Br, and this Br is 1.2 times 10 to the minus 2. Okay, and don't forget to square it. Okay. So if this was truly in equilibrium at these concentrations, this should equal to 1.1 times 10 to the minus 3 if this were truly in the equilibrium state where it's completely, equilibrated. So let's do this math and find out if this is truly at equilibrium. So 0.012 squared divided by 0.063, 0.0023. So something is not right here. 0.0023, which is 2.3 times 10 to the minus 3. 0.0023. So they are not equal to each other. This is a problem. They are not equal to each other. Okay? So 1.1 times 10 to the minus 3 obviously does not equal numerically 2.3 times 10 to the minus 3. So are we at equilibrium? Okay, so we are not at equilibrium. The question is, which way will the reaction shift to get to equilibrium? Okay, so we're going to put K second, and we'll put Q first in doing this Gator rule. So Q is 2.3 times 10 to the minus 3. Okay, Kc is given to us in the problem as 1.3 times 10 to the minus 3. 1.3 times 10 to the minus 3. 1.1 times 10 to the minus 3. And which is greater, Q or K? Right, which is greater, Q or K? Q is greater, right? 2.3 times 10 to the minus 3 is greater than 1.1 times 10 to the minus 3. Okay, so which way will the reaction shift? Okay, putting Q first, where do the alligator jaws go? The gators, where do the gator chomp go? To the left. Okay, so this is going to shift left to the reactant side. So shift left, okay, to get to equilibrium.
Dan, do we need to write that down? Like, there, like shift left, or can we just have like the?
Just say it's going to shift to the reactant side. Yeah, write that down. Okay, that way I know, you know which way the reaction is going to get to equilibrium. Yes, so please write it down when you have that reaction quotient problem on the test. So where will this shift? Okay, it's going to shift to the left. Okay, so to solve this problem here, number one, we'll set up the gator rule to determine which way the reaction shifts to get to equilibrium. Alligator rule. Step 2 now is to set up our ice table. Okay, set up ice table. So the ice table here is going to be ICE. Okay, I stands for initial, C stands for change, E stands for equilibrium, the final equilibrium concentrations. So BR is 1.2 times 10 to the minus 2. So that's the same thing as 0.012. BR2 is 6.3 times 10 to the minus 2. Where did we say this will shift, left or right? Correct, it's going to shift to the left. Okay, just like the previous ice table problem, it's going to shift to the left, but it's not going to be minus x. What will it be? And what does that 2 tell you? Minus 2x. Correct? Everyone see this? Okay, this will be minus 2x. What will this be? There's a 1 in front of the equation. This would be minus or plus? Okay, just plus x, because it's shifting this way to get to equilibrium. So at equilibrium, this will be 0.063 plus x and 0.012 minus 2x. So this is what's going to happen after the equilibrium is set. Okay. 3 is we're going to plug into equilibrium expression. Alright, so what is the equilibrium expression? Okay, we wrote it up here. We just plug in these equilibrium things and solve for x. So once again, Kc is going to equal to Br squared divided by Br2. Okay, so 1.1 times 10 to the minus 3 is going to equal to Br squared. That's going to be 0.012 minus 2x. Okay, whole squared. Okay, divided by Br2. What is Br2 at equilibrium? 0.063 plus x. right, so our final step here is to solve for x. Okay. And this is where the quadratic equation happens. So only up to here is what you'll need to know. Okay. See how good I am in the basketball. Oh yeah, all net. That was all net. Okay, so up to here is all you need to know. Okay. Because this requires the quadratic to solve for x, that's not something you'll be tested on because there'll be no quadratic on the exam. All right. All right. So just up to here, you need to know in terms of the math. Like I said, page 11 notes in terms of the math. But for us to get to x and solve for x, we have to use the quadratic, which will not be on the exam. So let me quickly just go over this. Okay, I'm going to move the 0.063 plus x to here. And when I do that, this will be 1.1 times 10 to the minus 3 times 0.063 plus x equals 0.012 minus 2x whole squared. Again, don't need to know this. A minus b whole squared is a squared minus 2ab plus b squared. So I expand that out. I distribute the 1.1 times 10 to the minus 3 times 0.063 plus 1.1 times 10 to the minus 3x. So anyways, I'm going to get it to the quadratic form. Since this will not be on the exam, I'll just skip all those algebra steps and I'll get it straight in the quadratic form. So the quadratic form here is a squared, just the quadratic form, 4x squared minus 0.0491x plus 7.47 times 10 to the minus 5. Okay, so I expanded this, distributed that, gathered my x squares, gathered my x, gathered my constant, and all of that equals 0. Okay, this gets plugged into the quadratic. Once again, do not need to know for testing purposes, but I'm going to go ahead and continue this. So we plug it into the quadratic equation. Anybody remember what the quadratic equation is? Good job.
I love that song.
A song? I don't know anything about a song.
Back in my math 2 class, my professor, she made us listen to this song every single day for the whole semester.
Okay. So I gotta check out that song then. It seems to work. Minus b plus or minus square root of b squared minus 4ac over 2a. I didn't have a song. I had to just memorize it as is. So lucky you guys. Lucky you guys. All right, anyways, not on the test, but I'm going to plug it in anyways. So the minus b, minus into minus is plus. This is 0.0491 plus minus square root of b squared. So if I take this b squared, it becomes positive 2.41 times 10 to the minus 3. Okay, that is this squared minus 4a. What's a? A is also 4. 4ac. C is 7.47 times 10 to the minus 5. Okay, all over 2a. Okay, what is a? Okay, again, a is 2 times 4, which is 8. Okay, this equals 8. All right, so you're going to get 2 answers for this. Okay, you're going to get 2 answers. Okay. One is 0.0491 plus square root of all of this divided by 8. That's one answer. And the other answer is 0.0491 minus square root of all of this divided by 8. Okay, so I went ahead and did this on our calculator. And we'll get 2 answers here. if you do 0.0491 plus square root blah blah divided by 8, you'll get the answer of 0.0105 molar. This is what x will equal to. Okay. Or if you do 0.0491 minus square root of all of this divided by 8, you're going to get 0.00178 molar. Okay, don't forget the units here. Okay, molar. So which one is it? Is it 0.0105 or 0.00178? Okay, what should we do? Okay, we'll take this x and plug it back into our ice table here. See? Okay. We'll take this x and plug it back into here. Okay. So let's test each of these values back into our ice table. Okay. So let's plug it back into the ice table. We got two answers. Okay, the first answer I will test is 0.00105. Okay, we'll test 0.00105 molar. Okay, so plug back into ice table. When I do that, I get a concentration of Br2 equals 2. What is it? Br2 is 0.063 plus x. So 0.063 plus our x here, 0.0105. Okay. .063 plus 0.0105, and this gives me an answer of 0.074 molar. Okay, so far so good. Okay, now what is the concentration of Br at equilibrium? Which is 0.012 minus 2x. I don't know why. Okay, let's plug in that value into this. Let's test the Br. Okay, which is 0.012 minus 2x. 0.012 minus 2 times our x, which is 0.105. And when I do this on my calculator, do you know what happens? I get a negative number. Okay, what does that mean? Okay, which is not our right answer. Can we have a negative concentration? Okay, so this is not our answer, because when you plug it back into the equilibrium, final equilibrium concentrations, you get a negative, and there's no such thing as a negative concentration. So now we'll test this value here of 0.00178 when we got our second value using the quadratic. Right, so now let's test 0.00178. 178. Okay, we'll first do Br2, which is 0.063 plus x, which is 0.063 plus 0.00178. And on my calculator, when I do that, I get 0.065 molar. Okay, that's good. All right, let's do Br. The equilibrium concentration of Br for this reaction is 0.012 minus 2x. 0.012 minus 2x. Okay, same as above. 0.012 minus 2 times, we're testing this value, 0.00178, and I'm getting 0.0084. this looks to be the right answer, okay, in terms of my final equilibrium concentration. Okay. So we have a way of really knowing if this truly and really is our correct answer. And how will we know if this truly and really is our right answer? How can we check our answer? Very good, by plugging it back in. And what should it equal? Okay, Royce, what should it equal? It should equal 1.1 times 10 to the minus 3. So let's check our answer by plugging it back in. So 1.1 times 10 to the minus 3 should equal to Br squared over Br, diatomic Br2. Okay, so Br, and we have to square that, that's 0.0084 squared. Okay, divided by Br2, we calculated that to be 0.065. Okay, we're checking our final concentrations. They should be at equilibrium. If they truly are at equilibrium, they should equal to the equilibrium constant according to the law of mass action. And let's check this out here. 0.0084 squared divided by 0.065. What do you guys get? Yep, 1.1 times 10 to the minus 3. 1.08, which is 1.1 times 10 to the minus 3. This is the right answer. Okay. So, like I said, for testing purposes, you probably want to know all the way up to here, and there's no quadratic on the test. But look how much work we had to do to solve this problem. Over here, and then all the way here. So that's a lot of math. Okay. All right. So that's the ICE table, and I want to say it again, just to reiterate, in terms of your test, your ICE table problem will be more like this. Okay, it will follow this format. All right, so let's move on here to the last topic of this chapter, and that is Le Chatelier's principle. We had a lab on this just a couple of days ago. I think everyone did really good on that lab, so thank you for that. So finally, I'll get to teach this to you. And the idea behind Le Chatelier's principle is let me read it, okay, and then I'll explain it. Okay, so Le Chatelier's principle. Okay, if an external stress is applied to a system at equilibrium, okay, at equilibrium, the system adjusts in such a way that the stress is partially offset. Let's underline this word offset. As the system reaches a new equilibrium position. So you disturb an equilibrium. Okay, the equilibrium is just fine. The reaction is just fine, and then you disturb it. Okay, how can you disturb an equilibrium? There's 3 ways you can disturb an equilibrium. We'll go through each of these 3 problems. How can you disturb an equilibrium? Yes? Yes, the first way you can disturb an equilibrium is to, good job, Susanna, is to change the concentration. Okay, either increase or decrease the concentration. So increase or decrease the concentration of reactants or products. that's 1. So what happens if you increase or decrease the concentration of reactants or products? Okay, remember the key word here is offset. What does offset mean to you? What does it mean to you, Royce? There's no wrong answer. If I say offset, what do you think it means?
I think that means you're kind of disturbing something again, or like you're making something change.
Change back.
Yeah.
Okay, so if you increase the concentration, where will the reaction equilibrium shift? Not to the side to increase it more, but to offset it. So it will shift to the side to decrease it. You increased it, so where will the equilibrium go? To the side that is decreasing it. You see what I mean? All right, so that's one way to disturb the equilibrium. A second way to disturb the equilibrium is to increase or decrease the pressure. Okay, this is important when we're talking about gases. Okay. Okay, so what do we say when we talk about pressure? See, gases are a big kind of a nuisance. Why do I say it's a nuisance? It's not really a nuisance, but you can express a gas in terms of concentration, or you can express it in terms of a pressure P. So we're going to worry about this anytime we see gases anywhere in our equilibrium. And then finally, the third disturbance we can do is we can increase or decrease the temperature of the equilibrium reaction. Increase or decrease the temperature of the equilibrium reaction. Okay, here we have to concern ourselves whether the reaction is endothermic or exothermic. So let's go over each of these examples. Okay, the first one, I think Susanna, our classmate, mentioned the first thing we can do to sort of mess up an equilibrium is to change the concentration. So I hope this comes pretty easy. Oh. Okay, if we add NH3, what is the offset of adding NH3? Okay, where will it go? Will it go to the side that adds NH3 or go to the side that removes NH3? You add NH3, where will the equilibrium shift? It shifts left. This is what we mean, Royce, when we say offset. You add NH3, it's going to shift left to counteract the addition of NH3. Okay. What happens if I add N2? Where will it shift? To the right. Okay, what happens if I remove N2? Where will it shift? I remove it. Where will it shift? To the left. Okay. Why? What's the offset of removing N2? It will go back to the side to increase the N2. Okay, what happens if I add H2? Where will it shift? To the right or left? If you add reactant H2. Okay, it's going to shift to the right. Okay. If you remove H2, where will it shift? Left. Okay. So if you increase the concentration of the products, it's going to shift to the reactant side. If you decrease the concentration of the products, it's going to shift back to the product side. Okay. It's pretty straightforward. Okay, don't overthink it. Okay. If you increase the concentration of the reactants, what's the offset of increasing the concentration? Decreasing the concentration. So if you increase the concentration of the reactant, where will it shift? To the product side, right. If you decrease the concentration of reactant, you remove a reactant, where will it go? Okay, what's the offset of removing it? The offset is for the reaction to shift to add it back. So it's going to shift to the left, okay, back to the reactant side. Right, so that's how you change the concentrations, you disturb the equilibrium. It just goes back to offset. Okay, the key word is offset. You add the reactant, it will move away from the reactant. You remove reactant, it will move towards the reactant. Okay. So that is changing the concentration of either the reactant or product. All right, the pressure thing is a little bit more tricky, and that's on page 14. What happens if you increase or decrease the pressure? So when we say increase or decrease the pressure, we're talking about gases, okay? We're talking about gases. Okay, this is condition number 2. Okay. Change the pressure or change the volume. Okay? So what does this entail? All right, so first of all, let's look at this reaction with me. Is this an equilibrium reaction? Yes. Okay, what else do we see here? What states do we have? Yes, we have gases. Okay. We have a gas, we have a gas, and then we have a gas. Okay. So let's say, here's how I'll do it. Let's say we do a disturbance, okay? Remember, gases can be a pressure or a gas, or a concentration, okay? A pressure or a concentration. So let's say the way I disturb this equilibrium is I increase the pressure. Okay, if I increase the pressure, what is the offset of increasing pressure? It will go to the side that has decreased pressure. Okay, very good. So which side here in this reaction, okay, in this reaction has decreased pressure? Is it the one with 2 moles? How many moles are in the reactant side? Okay, we have 1 mole of gas here plus 1 mole of gas B. So what's 1 plus 1? 2. How many moles of gas do we have in products? Okay, so decreased pressure. Which side has decreased pressure? The one that has 1 mole or the side that has 2 moles? Which has more pressure? Which one has less pressure? Okay, so this will shift to the side that has less number of moles because that is less pressure. 1 molecule has less pressure than 2 molecules. 2 molecules have a lot of pressure. Okay, they can hit each other. 1 molecule can't. Okay, so when you increase the pressure, this will shift to the side that has less number of moles. What else can we do besides increasing the pressure? Okay, we can decrease the pressure. Okay, let's say you and I, in this reaction, we decrease the pressure. Okay, what's the offset? It will go to the side with increased pressure or more pressure. Okay, which side in this reaction, which side has more pressure? The one that has 2 moles, which is the reactant side, or the one reaction that has, or in this reaction, 1 mole, which is the product side? So which has increased pressure? 2 moles, which is the reactant, or 1 mole, which is the product? More pressure. So this will shift to the side with more number of moles. Okay? That's if you decrease the pressure when you have a bunch of gases. So this will shift to the side with more number of moles. All right, anybody remember Boyle's law from Gen Chem 1? Boyle's law? All right, let's say I tell the class, hey everybody, let's not have class here, but let's move to the closet. We're going to have class in the closet. Okay? So what do you think has happened to the pressure? Increased or decreased? If we have class in that closet over there. Okay, that's a lot of pressure. We'll be shoulder to shoulder. We'll be bumping into each other. That's a lot of pressure. Okay, but what has happened to the volume?
It's reduced.
It has gone down. Okay, imagine this room versus the closet fitting all of us in here. Okay, so increasing pressure just is tantamount to decreasing the volume. Okay, if I want to increase the pressure on all of you guys and myself, I'm going to teach class in the closet. Okay, I shrunken the volume and I've increased the pressure. So increasing the pressure is the same thing as decreasing the volume. Okay, so increasing the pressure is the same thing as decreasing the volume. All right, so if you decrease the volume, which way will the reaction shift? To the side with less number of moles, because it's the same thing. Okay, if I decrease the pressure, it's the same thing as saying, class, let's not have lecture in this room. Let's have lecture in the football field. Okay, the football field. Okay, will that be more volume or less volume? Okay, more volume or less volume if we decrease the pressure. Okay. That should be more volume if we go from here to here. Okay. Let's say we have class not in this room but in the auditorium, which is room 220. Okay. More space or less space? More volume or less volume? Exactly like the football field. So we've decreased the pressure, which is tantamount to saying we have increased the volume. So decreasing the pressure is the same thing as increasing the volume. So if you increase the volume of an equilibrium reaction that has gases, it will shift to the side with more number of moles because it's the same thing as decreasing the pressure. Okay, that's shown here. Okay, so check out the highlights. Decreasing the pressure, okay, is the same thing as increasing the volume. It's all one and the same. Okay? So that is Le Chateliers' principle when we do our second disturbance, which is increasing or decreasing the pressure. Okay, the final way we can disturb Le Chateliers' principle, we can disturb an equilibrium, is by changing the temperature. This is condition number 3. Changing the temperature. So here we have to determine whether the reaction is exothermic or endothermic. Okay, so I'll write a reaction here. Okay, is this an equilibrium? Okay, check the arrows. It is an equilibrium. Okay. But let's say this equilibrium reaction liberates, okay, gives off heat. Okay, if it gives off or liberates heat, we call that an exothermic reaction. Okay, do we remember this from Gen Chem 1? Okay. So there's a term, and that's called enthalpy. How many of you remember enthalpy? Okay, Del P means heat flow. And for a reaction that gives off heat, the delta H will be negative. Negative, okay? This is in joules per mole or kilojoules per mole. Okay, negative. Is this exothermic or endothermic? Remember? Exo means outside, endo means from within, exoskeleton and such. So exo means it literally is in the outside, so it's giving off. So this is an exothermic reaction. Okay, an exothermic reaction. All right, so for an exothermic reaction, what is the value of delta H? Positive or negative? Okay, exothermic, the reaction is negative, so your delta H will be negative. So we can do two things to this. We can increase or decrease the temperature. Okay, what happens if we increase the temperature? Okay, where will the reaction shift? Okay, we're adding heat by increasing the temperature. Where will the reaction shift? Okay, increasing the temperature means adding heat. What's the offset to adding heat? Going to the side that removes the heat. So for an exothermic reaction, increasing the temperature will shift it to the reactant side. Shift left. What happens if we decrease the temperature? Lower the temperature. Okay, remove heat. Okay, where will the reaction shift? Remember, offset. So if you remove heat, it's going to go to the side to replenish or go to the side that has heat. So it's going to shift to the right. Okay, and this is the product side. Right, so make sure you know for an exothermic reaction, the delta H is negative. All right, so the opposite of exothermic is endothermic. And our delta H here is going to be not negative, but what value? Positive. Endo means from within, so it has to take energy from within. Heat here is a reactant in an endothermic reaction. Heat here is a reactant, and this is endothermic. All right, there's two things we can do to an endothermic reaction. We can either increase the temperature or decrease the temperature. Okay, so what happens if we increase the temperature? Okay, we add heat. It's going to shift as the offset to the right product side. Okay, our delta H is positive enthalpy, change in enthalpy for an endothermic reaction. And then what happens if we decrease the temperature? If an equilibrium reaction is endothermic, we remove heat. So it's going to go to the side to replenish, or the offset would be to the side that has heat because we decreased the temperature and removed heat. So it's going to shift the left reactant side. So that is the situation if the reaction is endothermic. Okay, endo means from within. All right. So where's heat in an exothermic reaction? The product side or the reactant side? Exothermic product side. Okay, you have to think exo means outside, outer. What is the delta H, positive or negative? Positive for endothermic, which means negative for exothermic. Okay, and then the Le Chatelier's principle works differently if it's exothermic versus endothermic. All right, if we add a catalyst, actually you saw this in the lab. Remember, you put the cobalt in the hot water, and it was one color. You put it on ice, it was a different color. Okay, this is pretty much the same thing. Okay, in your lab report, you determine whether it's endothermic or exothermic. All right, if you have a catalyst will not change the equilibrium. It's going to shift neither left nor neither right. This is the next important point here. Okay, so adding a catalyst does not shift the equilibrium. Okay? It just makes, as all catalysts do, it will make the reaction go faster. Okay. So it does not change equilibrium constant. Do you know what it does change? Okay, it changes the rate constant so that the reaction, boom, happens faster. Okay, so it doesn't do anything to the equilibrium. It just changes rate constant K, lowercase k. All right, so if you add a catalyst, which way will the reaction shift, left or right? Or neither? Okay, it's going to shift neither. Okay, will not shift. Catalyst does not change the equilibrium, and it will not shift. So it's not going to shift left. It's not going to shift to the right. It shifts neither. It just makes whatever's going to happen, it just makes it happen faster. Okay, but it's not going to make the equilibrium go this way or make the equilibrium go that way. Okay, so just know catalyst will not shift left or right. All right, let's see if we can. Well, we got 1 more minute left. So we'll do this Le Chatelier's practice problem. We'll do it on Monday, and then we'll review for the exam. Our exam is after spring break. Okay, so after spring break, and so Monday we'll finish this up. Maybe Wednesday we'll do a review for the exam, and also we'll start chapter 15, which is not on your test. Okay. The lab on Monday and Tuesday is on acids or pH. I've not gone over it in lecture, but I will go over it in lecture. So you'll just get a little bit of head start in the lab. All right, have a good weekend. Also, don't forget to turn in your homework. Okay, I'll put in the points.